All right, everyone, and once again, good morning and welcome to our webinar this morning. Today we're going to be discussing implementation of physics of failure into the design process. My name is Mark Musitano. I am a sales engineer here at DFR Solutions, and leading this webinar will be Dr. Nathan Blateau of DFR Solutions. Nathan has had extensive experience in the fields of physics of failure and with our Sherlock tool in terms of developing that, so he's very knowledgeable on the subject.
All right, well, good morning, everyone. Again, thanks for having me. My name is Nathan Blateau. I've been working at DFR Solutions since its beginning, and today I'm going to talk about really implementation of physics of failure into the design process. So, it's very inexpensive to make design decisions or changes during the design phase. If you identify a reliability risk and make the changes in the design and then do some type of simulation to verify that those changes will actually increase the robustness of the product, that's the least expensive technique for generating a robust product. So it allows you to make a much faster time to market because you're decreasing the number of redesigns that you have to do. If something fails a qualification test, you've already gone through a fairly large, lengthy development phase. You've gone through, prototyping, maybe even halt testing, and then something fails. You have to go back and redesign and repeat that whole process faster. So we're really looking at it as sort of interdisciplinary design team. There could be people doing reliability on the IC, the packaging. Usually, though, that's not what the end user is going to be dealing with. You're going to be dealing with, you've got the electronic packages, and how does it affect the PCB reliability. So it just makes everything go faster, and it actually makes it a lot cheaper to develop a robust product. So, there's a variety of levels of simulation and modeling. Thermal, mechanical, electrical, and then taking the results of those simulations, and this is really the more difficult part, how much stress is too much stress, how does that affect the reliability of the product. That's sort of where physics of failure and reliability comes into play. So you can develop very detailed models, but if you don't know what those results mean in terms of reliability, you're kind of missing out. So it's really very important to know, what types of stress levels copper vias can take, what types of temperatures your components can withstand, and then also, what types of stresses and strains that your solder joints can tolerate and still provide a robust electrical interconnection. When we talk about physics of failure, just sort of some definitions here, it's really, sort of understanding the science of what causes the failure to occur. So, understanding failure mechanisms, being able to evaluate life under actual operating conditions or during accelerated life testing. And again, really starting at the design phase stage, working physics of failure into it so that you have a robust product that will meet your reliability requirements. And then continuing through the life cycle of the product as things age or, predicting wear-out behavior in different field profiles. And then one of the hard parts is actually knowing what types of loads to apply. So there's a bunch of industry specifications. I'm not going to go into sort of the industry. I will touch on them a little bit. I'm not going to go into, what types of vibration loads, or thermal cycles that need to be applied depending on what type of use case you're having or what type of industry you're in. Again, it also goes into what your reliability requirements are. So, definitely the reliability requirements for a commodity product are going to be different than a medical product. So those are things we're not going to really talk about. So some definitions, and again, when we talk about physics of failure, we're looking really at wear-out mechanisms. It's very difficult to predict defects. Again, that's more DFM, designed for manufacturing, where you're looking at, do I have voids? Is my reflow profile correct? Am I forming good bonds? Those are very hard to predict as far as wear out. They will affect our wear out results. If something fails in what you think is a random manner, it may not be a random. It may be that you have such large defects that the stress levels in your joints are excessive and they're wearing out early. But it will look like a random type of failure. But again, the stresses that go into physics of failure could be thermal, electrical, chemical, moisture, vibration, shock, mechanical load, you name it. Really anything that can cause degradation or wear out behavior of the electronics needs to be considered. And again, premature failures are usually either excessive defects, cause sort of the infant mortality region. Gradual failures would be more wear out related. And then erratic could also be sort of defects that are not sufficient to cause infant mortalities, but now are at the floor of your bathtub curve. And we have lots of presentations on sort of the statistics and going over the different distributions for modeling these different mechanisms. But really, I'm a mechanical engineer. What I'm going to focus on are sort of mechanical effects on electronics. We really sort of assume that the electrical engineers know their job. They know how to make things function. Hopefully they're derating properly and making sure that their electronics can handle the current loads and the voltages being applied to them. But really, when something is missed, it's usually a mechanical reason. The board's not constrained right for vibration. It's being experiencing too much deflection during mechanical shock, and it causes things to break. Or thermal cycling is causing early fatigue of our solder joints because we selected the wrong component. Those are things that are a little bit more subtle, but have when we see large recalls on electronic products, usually a lot of times it's a mechanical reason. And it could be very subtle mechanical issues. It could be underfill materials having low TG. It could be bad plating on your circuit boards that's causing high stress concentrations in your plated through holes because it's just insufficient plating thicknesses. There's all sorts of different things that cause early failures. This is one thing I like to stress during any of my presentations is that unlike other materials, solder is a very poor engineering material. It's not dimensionally accurate. We're squeegeeing out paste, and so we get a lot of geometric variation. And one thing we'll talk about a little bit later on is small changes in dimensions can affect stress states dramatically for high cycle fatigue. Another thing that we accept with solder is fairly normal voids. And they're expecting, you can have up to 15 to 20% voiding. You can imagine if that was an I-beam on a structure made out of steel, and you had a 20% void, that would be a major issue. And it's one of the few materials that is really being used in a regime that you would never use any other material, at least any metals. It's constantly being subjected to inelastic deformation, so you're plastically deforming it or permanently deforming it. And again, no, you wouldn't use steel, titanium, or aluminum under those conditions unless you really want it to fail. But it still plays into the role during vibration. We need to prevent those types of inelastic deformations or plasticity during vibration events, really because of how rapid those types of events are. But again, because we're using this material in a regime that you don't normally use metals, it makes the electronics reliability fairly unique in that regard. We're using a metal in a regime that a standard structural engineer said, hey, you can't do that. Well, we have to do that in electronics. First thing to talk about, we're going to go over some design considerations for vibration fatigue. As I mentioned, we have to avoid inelastic deformations at all costs because just the rapid rate, when we have plasticity or creep, those are what we call low cycle fatigue. We're talking less than 100,000 cycles to failure. So we're accumulating inelastic deformations, things fail very quickly. So just an example of how quick that can occur, if I'm going, if I put something on a compressor that's, for some reason getting 60 to 100 hertz vibration, 100 cycles per second, you're looking at failure, 16 minutes to get 100,000 cycles. So that's usually why, if you are doing a vibration analysis and you see any type of plasticity or inelasticity, that's a showstopper. That product cannot be used in that environment because it's not sufficiently constrained and it's going to fail very quickly. So that's really, when you do a vibration analysis, it almost gets down to sort of pass-fail, because if I get any plasticity occurring, things fail almost instantaneously. Once I prevent that, I go to an elastic, and now we're talking, tens of millions of cycles to failure. So there's a really abrupt transition between pass and fail during vibration. The one other thing that you need to be concerned about for vibration, and again, I would definitely recommend getting Steinberg's Vibration Analysis of Electronics Equipment book. It's really sort of the go-to reference for anything vibration related for electronic equipment. But he has a good rule in there, is what we call the octave rule. And an octave is a doubling of frequency. So really, you do not want your printed circuit board natural frequency to be within 2x of the chassis natural frequency. So what will happen is you'll get coupling between the two and you get large amplification factors. It could be 20, 100x of amplification from the input vibration to what gets subjected to the circuit board, because you're hitting resonance of the chassis and resonance of the circuit board, and they build on each other. So it is important that during vibration you have a good separation between those natural frequencies. How do you determine what the natural frequency of your board is, during the design? You can do it by hand, but again, this is from Steinberg's book for sort of simple shapes, square, rectangles, triangles, circles, hexagons. Yeah, hexagons. But again, these don't really represent shapes of standard circuit boards. So really what we want to do is, FEA analysis, but using an FEA tool such as Sherlock that allows us to do that very rapidly. So, you can use Sherlock, you can use Abacus, ANSYS, Nastran for doing vibration analysis of your design. There's really a lot of factors that we can adjust during the design to impact the frequency response of that circuit board. It could be component placement, boundary conditions, printed circuit board properties. And you see, usually, if I were to rank these as far as effectiveness of changing the natural frequency of the board, boundary conditions number one. Then component placement, and then PCB properties. Really, if you're just modifying the PCB properties a little bit, you get it doesn't affect the natural frequency that much, but it does impact it. And we'll show some examples of that. You do have to consider, component mass and heat sinks and the printed circuit board properties and how they affect the natural frequency. But what really, the rule of thumb is typically the higher the natural frequency of the board, the more robust the design. So it is, we're really targeting, and I think usually I'm shooting for 150, 180 hertz as sort of a starting point, because, a lot of chassis are usually around, I would say 50 to 100 hertz. So we want to get 2 octaves above that, depending on what your chassis stiffness is. You need to have a fairly stiff circuit board. So usually if I see something below 150 hertz, I'll flag that immediately. In this particular case, this is sort of a PCIe type of circuit board, has a heat sink, and right now it only has a couple of boundary conditions. Some of these connectors and this edge connector have mount points on them. And you can see, 23 hertz. This probably would fail during transportation very quickly. Just even small vibration inputs would cause problems with this board. So we definitely need to make some changes. So I just wanted to show you how quickly you can make changes. Here is sort of, we've overlaid the deflection, and this is done automatically in the tool. So this is the current boundary conditions. We've got some boundary conditions on these connectors, sort of the backplane screws. The edge connector here. But the first thing is, okay, I know where my high deflection regions are. Okay, let's just add a support there to prevent that from happening. And then I just go in, select that in the tool, and add a mount point there very quickly. And then I can quickly rerun the analysis and say, okay, just adding one mount point to my board quadrupled my natural frequency. So again, we were at 23 hertz. Now we're up to about 82 hertz. So, a significant impact. And that's why I said boundary conditions are really sort of the first order effects on the natural frequency of the board. Another thing is we have a heatsink here. I can quickly change that from copper to aluminum. Copper, I think, is a density about 6 to 8. And then aluminums are really a little bit over 2, so I think it's like 2.6. Off the top of my head, it's around there. But we can reduce the mass of that heatsink considerably and see how that affects the board response. Again, we get about 11 hertz bump. Now we're up to 93 hertz by just changing those heatsinks. And now I could do a little bit more. I could change the fin or change the base plate thickness, anything necessary to sort of reduce the mass of that heatsink to try to see how it affects the natural frequency. But looking at this plot, we can definitely see we still have a high deflection area at the bottom corner. Again, right now we're doing simple boundary condition changes, but I could actually add another mount point. So I added another mount point down here. I also increased my printed circuit board thickness to 1.5, from 1.54 to about 1.6. Now you have to be very careful. I mean, changing printed circuit board thickness can impact a lot of other things. So, if it's a controlled impedance board, it's something that has to be considered once you start increasing thicknesses. Again, this has got an edge card connector. I got to make sure that my printed circuit board within tolerance can still fit within my edge connector. So there's a lot, you can't just change these. You have to actually, change them or, check with the electrical engineers, check with the mechanical engineers to make sure, what can I do to the circuit board as far as thickness. But as you think about it, it's a really competing mechanism. As I make the board thicker, the stiffness of that board increases dramatically because it's based on the moment of inertia of the board, but I'm also have to fight against the additional mass of the board. But mass only increases linearly. Stiffness increases as a power law by the moment of inertia. So, we're at 108 hertz. It's still on the low side. Again, this is sort of a PCIe card for a desktop type of application. It's not a mobile card. 108, 109 hertz, probably okay for a very benign vibration environment. Really, we just have to survive shipping. So let's just assume that 108 is fine. Next thing is actually to conduct. I don't want to, there's no reason to conduct a physics of failure assessment. You have to sort of look at, 23 hertz is really low. I'm not going to conduct a physics of failure assessment until I get my natural frequency of that board to something that I think is acceptable, just based on experience. And I would say getting over 100 hertz, depending on application, is probably a target. One thing is, remember, as we said before, during vibration, we have to avoid any type of plasticity or inelastic or nonlinear strains. So during vibration, we're going to assume that things are, now we're into the elastic regime. And once we get to elastic, things are, are linear. So that now I can say, well, if I bend the printed circuit board a certain amount, I know that that's going to be proportional to the strain in the solder and the strain in the leads. So that allows us to make fatigue predictions based on board level strain. So, we're not typically modeling solder joints when we're doing a full board FEA model. We're modeling components and simplified structures. If we want to, we can model leads, and I'll show you that in a little bit. But we're really relating board bending to fatigue predictions. And people that are familiar with Steinberg, he had one where he related board displacement to fatigue. We take that a little bit different approach where we go, okay, a BGA or a surface mount part is really more susceptible to bending than board displacement. And we'll show that, I can have areas of large board bending that really have zero displacement. So that's just another drawback of using a displacement criteria versus a board strain or board bending criteria. Really, two types of things that we're looking at. There's for very tall components or components with large mass with compliant leads, you do have to look at component motion. Under certain cases, high frequency, you may get the components sort of exciting the components independently of the circuit board. Or if and these are just some examples here, that this component was sort of wiggling back and forth, causing fatigue cracks right where the joint enters this, right where the lead enters the joint. Here, the board's bending and it's pulling on this lead and causing a lead failure. So definitely, if you have any large components with leads, you want to go the extra step and add detail to the FDA models to account for those leads. So again, I'm going to stress this one more time. Low cycle fatigue is, creep and plasticity happens very quickly. When we're talking about high cycle fatigue, it's really a stress law, elastic. So you can see here, this is sort of the SN curve. We're talking about things down here for vibration. And you can see very small changes in stress or elastic strain can have large impacts on time to failure. So that's just I can change my stress a little bit, and it can have order of magnitude influence on time to failure. Just be aware of that. Some typical vibration levels that we want to look at. There's harmonic, there's random, and most of the people, typically it's a random type of profile. I just picked a random profile here in the lower right. It's a PSD curve. You enter it directly into the software. It applies that as a base motion, and you can change it in what axis it's being applied, and then it applies it to the circuit board. So just there's a lot of military standards and SAE and ASME type of standards that you can rely on for various vibration profiles. But typically it's transportation related. Any mobile products. Usually for most of the industries it's transportation, and then things are mounted somewhere, unless it's going into a mobile application where it's going to be totally different. But usually it's transportation related. So physics of failure, again, this is the results for that circuit board I showed earlier. This is the PCIe circuit board. And this is actually kind of difficult to get when you actually see, when you really run a vibration fatigue, you may see a straight line down here, meaning everything's good, or it fails very quickly. Because, again, we can rack up 100,000 cycles within a matter of minutes. So, don't be surprised that, and this goes back to, if you go look back at Steinberg, it was more of a pass-fail type of criteria because of this behavior. In this particular instance, we are seeing a slight fatigue curve here, but again, this BJ, this 1136 BJ, which is a fairly large BJ in the center of that PCIe card, is failing. So these are the types of outputs that you would get from a physics of failure type of analysis for vibration. And now we need to go back and we need to look at that circuit board and say, okay, why is U1, which is in the center of the circuit board, failing? These red areas are areas of high bending. So this part is failing because on either side of it, there's large amounts of bending. We really have to do something extra to prevent this from failing in that environment. So, it could be adding another mount point, which, we've already added two, one up here and one down here, or we could add stiffeners. But there's more work to be done. And again, we're doing this in the design stage. We've got the layout, preliminary layout. We can, make some changes. We could try moving U1 to see if that affects. Maybe the one thing that you see is usually what you'll see is what we call alleyways or areas where parts are not overlapping, which allows the board to sort of hinge and so all my bending is taken up in a specific location or concentrated. Those are types of things that you want to look at in your design, saying, well, can I prevent a sort of a hinge from forming by either moving components so they overlap, maybe you shift U1 to the left so that it's sort of shadowed by these two components on either side, and that may help prevent this sort of hinge from forming. Those are all things that you can use the FDA tools to sort of see if that's occurring. When we talk about mechanical shock, it's very similar to vibration. Typically, higher natural frequencies is directly related to how stiff the board is. The stiffer the board, the lower the deflection during the shock event. We are also looking at what we call overstress failures. And another thing about shock is that when you shock a board, you typically are yielding the solder joint, causing plasticity. And what'll happen is, and it's interesting about electronics, is that the yield stress of solder is pretty much right on top or overlaps the overstress limits for a lot of the packaging materials. You get, and it's, bond pad cratering stresses, ceramic capacitor cracking, are all within that sort of 40 to 70 megapascals. So what you'll see is that, when you have a shock-related event, you'll cause sort of mixed mode or different types of, the failure sites will be sort of, it may be bond pad cratering, it may be intermetallic fracture. So here's an example of intermetallic fracture, where in this case, this is a tin nickel intermetallic, now, which fractured. Again, I don't know if it's really a design decision whether or not to use OSP, ENIG, or immersion silver, immersion tin as a plating finish. It's more of a DFM type of issue, but it can affect your shock robustness. And it's something to be considered when you're writing up your documentation on printed circuit board requirements. Do I want to go to ENIG in a high shock environment because I know ENIG has weaker intermetallics than OSP? It's just sort of the nature of the intermetallic that forms, a tin nickel intermetallic versus a tin copper intermetallic. But you can see here, during a shock event, I can fracture the intermetallic, or I can cause bond pad cratering. If this is a large ceramic component, I may fracture the ceramic. It's just that, and it got a little bit worse with lead-free because now we have a stiffer solder joint that transmitted more stress into the other interconnect structures or even the bodies of the components. So just something to be aware of. But typically, anything I do to increase my vibration fatigue performance is usually going to help my mechanical shock. In this particular case, this is an example using the Sherlock tool of mechanical shock sort of in plane of the circuit board. So this circuit board was dropped on edge and the component is shifting. And in this particular case, under repeated shock loads, we are actually getting high enough strains due to that component movement to fracture the leads. So again, as I said before, for large components and like electrolytic capacitors that are tall, large ceramic quad flat packs such as this, it may be necessary to go down to the detail of actually modeling the leads so that you know how that part is moving for your expected field environment. And maybe you can't use that type of component in this application because it's just too massive. Or I have to stake that part. I may have to quarter bond that part to keep it from moving. Again, this is shock and board thickness effects, but you can imagine this is sort of the same thing for vibration. If I say, okay, with a 1.5 standard thick board, I'm getting almost a millimeter displacement. If I increase my board to 1.8, I cut that down by about 30%. Again, if I even go a little bit thicker, I can reduce it almost to 50% of the baseline. or more than 50%. So, this is just some effects of board thickness. You can use it. It takes a lot more. Yes, you're increasing the mass of your circuit board, but again, your stiffness is increasing at a faster rate than your mass effects. So, board thickness can be used to sort of give you a little bit more robustness with regards to shock. When we switch over to thermal cycling, using Sherlock during design for thermal cycling fatigue, some examples of that are different types of package selection, printed circuit board properties, solder pad design, and plated through holes. Those are sort of what we're looking at are things that wear out or fatigue during thermal cycling, and really there's really two weak points. It's going to be the solder. It's going to be your plated through holes. I don't think I've seen any other. If I see copper fatigue on like other leads or during thermal cycling, it's very rare. It does happen, like some large pin grid array components. We have seen lead fatigue, especially on a very large pin grid array. But it has to sort of unique. We're talking like a 50 millimeter pin grid array on a very thick FR4 type of circuit board where you're actually getting large distance neutral point bending of the pin grid. So just some basics on the physics of failure behind solder fatigue. Really, Engelmeyer was the first one that came up with this. And it may have gone back even further, and it's a standard type of model. But really, we're looking at sort of a semi-empirical type of analytical approach where, fatigue data in general is empirical. I put something in the oven, I thermal cycle it, I get a time to failure. There's really not any physics that has been developed to the point to, like, at least for solder, to make fatigue predictions, based on, actual material characteristics of the solder without having some type of test data to back it up. People have tried on grain size and growth and stuff like that, but usually when it comes down to it, we're looking at taking fatigue data and using distance neutral point or distance neutral point based type of model and extending that test data to other configurations. If I have a 2512 resistor and I have the fatigue data for that, can I use physics of failure to extrapolate to a different size ceramic resistor? So can I go from a 2512 to a 1206? So it is, distance, the length of the diagonal length of the part, the height of the solder, differential CT mismatch between the two components. The temperature change gives you some type of strain range. In this case, it's shear strain. There's correction factors, but typically thicker the solder, smaller the part, the longer time to failure. Here's just a slight modification where we add stress effects to the solder. Taking in more, instead of just assuming that the component is infinitely stiff and the board is infinitely stiff, actually looking at stiffness of the board, stiffness of the component, taking in lead effects, just more complex sort of stiffness type of equations to look at compliance, to look at reducing the load on the component. And then we take whatever the results of that are, and we go into sort of a Moreau-based energy model that gives us cycles to failure. So it's just some basics. There's a lot of, we've talked about this quite a bit in past presentations. I don't want to really focus on it here, just to give you some brief overview of what we're looking at. When we're looking at, what these cracks look like, and, can I pick different types of components for my application? This is a design consideration. Am I going to pick a 2512 because I need the power dissipation? Can I pick a 1206? Even 0603s or 0805s. These are all things that need to be considered when you're laying out that board, when the electrical engineer is picking those components. And as I said before, usually larger solder joints perform better. These are some examples. Here's a BGA fatigue crack, ceramic chip resistor fatigue crack, and even this was a optical isolator with a copper lead frame that was failing. So component selection, 2512 resistor or a 1206 size resistor. For aerospace, I would say there's a lot of historical knowledge on using these ceramic components in, sort of very severe thermal cycling environments. But even for moderate thermal cycling or, outdoor environments, can I use a 2512 or do I have to consider a smaller size? So just, here is a comparison between the fatigue behavior of a 2512 resistor versus a 1206. I'm just showing you sort of the life curves. You can see, I think I applied 1,000 cycles. The 2512 is failing. I would say characteristic life is, 800 or 900 cycles, where the characteristic fatigue life of the 1206 is probably closer to 3,000, 4,000 cycles. And just some physical differences. So definitely physics of failure can, you can use the, there's some standalone tools in the Sherlock software where you can actually make these types of decisions on components. Here's just an example of that. So, we're going to stick with the 2512 and we're going to look at, all right, what happens if I increase the bond pad length from 1.28 millimeters to 2 millimeters? And that may be necessary definitely for power devices. You want, increased thermal sort of areas to decrease the thermal resistance. So usually you will have larger pads on power devices than just a small signal device. So going from 1.28 millimeters to 2 millimeters, I get a 54% increase in life. So this is the standalone tool. Well, it resides up here in the menu bar, solder fatigue, and I can just quickly change some parameters on my bond pads and see what the effect of is on life. The other thing I can do is look at, well, do I have to pick up better laminate? If I have a printed circuit board that is some generic FR4 that has a fairly high CTE, such as 16 ppm, which I would say is more standard. Most circuit boards are going to be within the 16 to 17 ppm range. Do I want to pick up better material that has a lower CTE? So, going from 16 ppm to 15 ppm on the expansion of the circuit board. And again, the stack-up tool in Sherlock can actually give you a prediction of what the CTE of your boards will be, during selection. But I get a 26% increase in life. If I further decrease that to 14 ppm, and that's achievable, I get even a much larger increase, almost 63% increase over baseline. So yeah, I can, if I need to use a 2512 resistor in my design, I have to look at other things. I have to look at increasing the bond pad dimensions. I have to look at going to a more expensive laminate. It may just be easy enough to say, hey, let's just put two 1206 resistors in that location in order to handle it, to have the same power type of rating. I have to see if two 1206s actually can handle the same power as a 12512. But that may be necessary because in order to get a 2512 to work in this design, I have to go to a much more expensive laminate that has a very low CTE. That's probably the main thing. And I have to increase my bond pads. I may not have the real estate around these parts to make the bond pads much larger. Another thing that can be influenced when we're talking about thermal fatigue are the plated through holes. PCB thickness, plating thickness, hole diameter. These are all design decisions. What size holes am I going to use? I would say, aspect ratio is one of the key drivers. The smaller diameter of the hole, the less fatigue resistant it's going to be. So, go to the larger holes. It's easier to plate. It's easier for the printed sort of board shops to drill. and to make sure that you don't get the chemistry, make sure they do get the chemistry in there to plate it right. But I definitely, if you have the choice of going with a larger hole, do it, as long as you can fit it into your design. When we look at plated through-hole fatigue, usually there's two different models that we have implemented. There's the classic IPC TR579 model that's, looks like it was developed back in 1988. And again, this is Engelmeyer, who's, pretty much had his fingers in a lot of different pies as far as reliability of electronics. He did most of the work on the model that is in IPC TR579. And it's worked quite well. The thing is, it tends to be a little bit overly conservative when we start getting to larger plated through holes. But here's some of the basics on that model. Again, it's easy. If you want to spreadsheet this model up, you can do it in a spreadsheet. You can do it for a single hole, one hole at a time, to try to figure out. And it may be sufficient to do it that way. But we have implemented it into the Sherlock tool to make it a lot easier. You can use it as a standalone tool, like I showed with the solder fatigue calculator, or I can, assess all the different plated through holes on my circuit board. Here's just an example. What causes plated through hole fatigue is really the Z-axis expansion of your circuit board. The hole diameter. So, as that board heats up and cools down, it expands through the thickness. That's what we call the CTE in the Z direction. Usually that is much higher than the XY plane. In fact, it's, 3 to 4x higher. So, even though, it's a fiber reinforced material and it doesn't really have fibers in the Z-axis, everything's in plane. So there's not a lot of constraint in the Z-axis, so the epoxy wants to expand, you're going to get a very high CTE in the Z direction. That causes a lot of stress on the copper vias. The other model that's been implemented into the software is the IMEC plated through hole fatigue model. This is an alternative model, and what we've seen is actually it provides much more realistic results when we get to larger plated through holes. So it is a more modern model. It's not from 1988. It's got a lot more, FEA validation behind it because realistically, in 1988, they weren't doing a lot of FEA on plated through holes. So this is a more modern model. One of the things I like about this model is it's sort of, with the IPC TR579 model, there are some calibration or correction factors that the user has to sort of know something about plated through holes in order to determine. So that's this KD and KQ. And again, definitely read the IPC TR579 documentation. It's a good sort of background on the physics of failure of plated through holes. But there is some engineering judgment when picking some of the correction factors for it. The TR57, the IMEC model sort of gets rid of those for you. So it's a less, the engineer doesn't have to sort of make these judgment calls on what he thinks the quality factor for these plated through holes are. So just examples of plating thickness effects. If I go with an IPC class 2, which I think says about 18 microns at the thinnest location, so overall like 20 to 24 microns of thickness, I get 1,621 cycles. This is the IMEC PTH fatigue model. And I'm keeping the printed circuit board properties the same here. It's just changing the plating thickness on the walls. So go from 20 to 30 micron thick, I get a significant increase in time to failure. So that's another sort of design change. Printed circuit board thickness, thinner the circuit board, the lower the aspect ratio, the longer time to failure. So again, another significant impact. So one of the things you have to consider is as I make if I'm increasing my board thickness to gain mechanical shock or vibration robustness, am I now kicking myself because I'm putting more stress on my plated through holes? Those are all things that you need to consider during design that, hey, I can't just arbitrarily increase board thickness to solve one problem without impacting something else. Again, another strong, in fact, influencer is coefficient of thermal expansion in the z-axis of the board. So, some generic laminates, especially if they're non-filled resin systems, have very high z-axis expansion, 60 ppm. I get 1,293 cycles. If I go to something like an Isola that's more Isola 370HR that has more like a 45 ppm, almost over 2x improvement in cycles of failure. And the accuracy of these physics of failure-based models are really good. You're talking about models that are really based on, explaining empirical behavior, such as fatigue, with, understanding the physics behind it, or trying to, we don't know exactly what is a grain boundary sliding or void coalescence in the solder, or is it, that's occurring, but, do you really want to model that? Or do we can say, hey, the length of the part, the thickness of the part, the materials of the part can explain my fatigue behavior. So these are just some examples of the accuracy of these types of models. And really, what physics of failure gets you is this is a classic, design, build, you test, did something break, you fix whatever breaks, and you sort of repeat this type of loop until you run out of money or time. What physics of failure, and I tried to figure out how to best put this in here. Really, during design, we're analyzing the design using physics of failure. We make sure that it's going to pass our qual test. We make sure it's going to pass hopefully predicted to pass our qual test and predicted to meet the field requirements. We do have an issue, if my qual test doesn't, if I'm not analyzing field environments and I'm just looking at qualification testing type of criteria, there is a possibility that, if you don't know your field environment, your qual test may not be sufficient for the field environment. So it is possible to still, even if you do a POF on qualification type of loads, that you could still have a field issue. That's why it's very necessary, and in fact you can still do it at the design phase, is to understand what the field environment is, understand your qualification test stresses, and make sure that those two are aligned so that any qual testing I'm doing sort of matches the type of damage or the loads I expect to see in the field. So we're doing design and POF at the same time. We build it. We're not eliminating test. And, you're still going to have to show that this product, is qualified and meets your requirements. But what we're doing is we're reducing the number of times you go through this loop. So I want to go through this loop once. I don't want to have to go through to fix anything. I want to go right through to false detected no, and I have a robust product. And it's been demonstrated that physics of failure. We have some test cases or ROI type of studies that yes, physics of failure has been demonstrated to get us through this loop. I don't have to have a Rev 2 or Rev 3. I can get through on a Rev 1, pass my qual test, and reduce this time and money and save a lot. Shorter time to market, less money during test, get through the loop, or not even have to get into the loop and get through it the first time. And with that, I would like to say thank you, and I'll take a look to see if we have any questions.
Yeah, thanks, Nate. Really great job on the presentation as well. I do have the questions up here, if you'd like me to read them off to you, and then we can answer them one at a time, if that's all right with you.
Okay, I can... it looks like a lot of them have been answered. Right, okay, so one of the questions, and I'll just sort of reiterate this, can Sherlock handle electrical stresses? As I said sort of during the presentation, we really are relying on the electrical engineers to make sure that they derate it properly. That being said, there are tools in Sherlock that you can enforce derating, based. But again, these are electrical stresses. in order to get electrical stresses, you have to do almost like a spice analysis or enter in voltages for those components. But no, Sherlock Honest does not do any electrical analysis on your circuits. It's more of a spice type of analysis. But there are places in Sherlock to enter electrical stress data that can be used for D-rating analysis. The next question is Sherlock capable of performing vibration and thermal cycling combined loading for solder joint leg prediction? Currently, no. We're working on that, and we've done a lot of testing here to get that type of information, because usually when people are doing vibration testing, they're not doing it in a thermal chamber and getting different fatigue parameters for the solder. We see Hull testing, which is very limited as far as what is the fatigue behavior of the solder. But we have done that testing. It is something we are working on putting in the software, where you would specify where in your thermal cycle the vibration is occurring, and Sherlock would have to run multiple FDA analyses to determine that, because we have a lot of material property changes that are going on. Your printed circuit board is getting stiffer at the cold temperatures. Your solder joints are getting stiffer. And what we have seen during our testing is, because at cold temperatures the solder is very hard, your printed circuit boards are hard. For the same vibration input, you're getting lower deflections, lower board level strains. At the cold temperatures, things last a lot longer. On the hot side your board is softer. You're getting larger deflections, more strain is going to the solder. Things fail very much sooner. So we do have the information. We are working on it. It really comes down to GUI and how to sort of structure that user interface. For IPC TR579, for thermal shock, theoretically copper is fairly insensitive to ramp rates. We're working in sort of there's not a lot of temperature dependency on the thermal ranges that we're dealing with. If I was going up to 600 degrees C, there's something to be worried about that. My only question, the only problem with thermal shock is really thermal gradients and making sure, I'm not getting some weird bending behavior because I've got, one side of the board is getting hot versus one side of the board is getting cold. Really, I would say the limitation for IPC TR579 and any sort of FDA tool would be you're looking at isothermal conditions. You're not being able to take into thermal gradients being imposed on your circuit board during the temperature change. So really, I would say once you get over, a ramp rate of 10 seconds from -40 to 105, you're pretty much taking something from some type of fluorinert type of fluid, and you're just plunging it back and forth and liquid to liquid in that regard. I'd be concerned that the models are going to fall apart, and we've seen that. So anything really over, that's just pushing the models. I would say I'd be wary of making predictions with any tool with a liquid-to-liquid type of thermal shock condition. Tin whiskers. We have a question. Discussion on tin whisker defect with Sherlock modeling. Tin whiskers, it could be sort of considered a defect, as you say. I mean, if the plating is done too fast and you build up a lot of residual stresses, you can form whiskers very quickly. The one thing you could, and we haven't implemented it yet in Sherlock, is actually look at lead spacing and look at, we have if you have a net list, we know where all the leads are. We can actually look at sort of a distance thing. But now getting into actual prediction of tin whiskers is very difficult, and I'm going to sort of punt on that for now, because really it's a plating defect, and you can make some types of predictions, but usually something goes wrong with the plating solution, you get lots of whiskers. Can you talk about how to implement? Here's another. Can you talk about how to implement this into the design process? For example, would it be a good idea to hold PCB builds until after a check using Sherlock? Are there other major points you and your team would have found useful to others in the industry? I would say probably, you want to run your Sherlock assessment before the printed circuit board build. I know that's, you printed circuit board. Yeah, I would say you want to have it prior to the PCB build. Hold off on building the printed circuit boards until after the Sherlock assessment to make sure that, I don't have to change laminate materials or something like that. I can't really go into that right now as far as we're kind of running out of time. We'd have to, we'll take an action item to address this, Cliff, and Mark. We'll have these questions, and maybe we can respond with a more detailed answer there. Can a user create a design for experiments in Sherlock by defining variables for parameters? Right now, we do not. We do have scripting in Sherlock that we use for testing. We have not sort of exposed that interface to the user. It is very rapidly, I can look at different solder thicknesses, and how that influences. I can look at different pad geometries. But right now we can't say, hey, I want to automatically vary the solder thickness or solder stencil thickness from 4 mil stencil to 8 mil stencil and look at the time to failure changes for all my parts. We haven't done that yet. It is something we are looking at doing. Sort of this, sensitivity analysis to look at, how for DOE. Whether this is I got another question here. Burnin Test is Burnin testing essential for all automotive electronics? If yes, what kind of stresses need to be applied? When we're talking about burn-in or screening, there are different things to look at. I can't, this is a broad topic. There's lots of different types of burn-in stresses. Or I would take it one step. I wouldn't say just burn-in. I would say it's screen. And yes, some people will screen automotive product, run it through. I definitely recommend some type of thermal cycling. Sometimes people will do a HAS or using a Hall chamber to do a highly accelerated stress screen. That's low-level vibration being applied to just look for defects. But any type of burn-in, really, what you're looking at is trying to screen out defects. But one thing that is usually good at screening out solder defects is a few severe thermal cycles, minus 40 to 125, 4 or 5 cycles. A high temperature or an elevated temperature screen to look at maybe a defective component if there's any die issues. But yeah, depending on where the product is going into the automotive, into the vehicle, will depend on what type of screening you do. But yeah, that's a very broad question, and can't really address it fully here, or even scratch the surface. But definitely, Jim McLeish, our automotive expert, can give you guidance on what types of stresses need to apply for efficient automotive burn-in testing or screens of electronic product. The last question, we're pretty much out of time. How feasible to use Sherlock simulation for prediction of reliability of sensor device with brand new technology with little field information? All right, so again, Sherlock and any type of sort of these physics of failure are most valuable when we have empirical data behind it, because we know what's going on. With new geometries, new technologies, we really like to go to more, detailed FEA modeling of a single device, and then and then make some type of prediction on that. It's really, it's not a mature. It's very difficult to do physics of failure on that type. Now, if it is a geometry that's similar to an existing device, I would say yes. I mean, if it's just a slight variation on a BGA type of device or something like that. But if it's a totally new device with new geometries inside or some type of interconnect structure, we definitely have to go to like a 3D FEA on the device and do a detailed model of it. So yeah, it wouldn't be something. Yeah, I can get a little bit, with Sherlock as far as new technology, but really we're looking at a detailed FEA study at that point. We're looking at the sort of a follow-on question for the combined loading for the solder joint life prediction. I would say, again, because what we're looking at is multiple FEAs, and the finite element runs in Sherlock are relatively quick. There's, I would say on average it's 10 to 15 minutes for each type of vibration simulation in Sherlock. But once we were sort of quadrupling it or tripling the number of FEA runs when we start putting in this temperature-dependent vibration. We have the data necessary. I would say probably early next year we're looking at getting that type of, actually early next year is coming up very quickly. Maybe second quarter, end of second quarter next year would be sort of the timeline we're looking at that for getting that temperature dependency in. With that, that was the last question. We're out of time. I'd like to just again thank everyone. I'm going to turn it over to Mark for some closing.
Okay, great. Thank you so much, Nate. Thank you all so much for attending with us, and have a great day.